Welcome, Chemistry 1B, Unit 5, Video Example 3. We're going to learn a method called the method of initial rates, where we can determine the rate expression for a particular reaction. Okay, so in this sense, we see we've got 3A plus 2B goes to some products, and we want to set up the rate equation such that we can say the rate is equal to the rate constant multiplied by the concentration of A raised to some power M multiplied by the concentration of B raised to some power N. Okay, so how do we determine M and N? Well, we need some experimental data, which we are seeing on the screen at the moment. We have 3 experiments where we vary the concentration of A, and we also vary the concentration of B, and at each experiment we determine the initial rate of the reaction. Okay, so it's convenient for us to set these things up so that when the concentration of one species is doubled or tripled and the concentration of other species are held constant, we can then tell the effect of the varied species on the initial rate. So let's look at how we can do this. Okay, so let's first look at experiment 1 and experiment 2 and see what's happening. We see that between experiment 1 and 2 in A, right, we have experiment 1 has a concentration of 0.1 molar and experiment 2 has a concentration of 0.2 molar. So between experiment 1 and 2, the concentration has doubled. Okay, if we look at concentration of B now, we see that the concentration of B has remained the same. And if we look at the value of the initial rate, we see that something has happened to the initial rate, going from 1.2 times 10 to minus 4 molar per second to 4.8 times 10 to minus 4 molar per second. Okay, so when we compare these two experiments, we see that the rate increases 4 times, or we say that it quadruples. Okay, so by doubling the concentration of A, it quadruples the rate. And effectively then the reaction is second order in A. And how do I do that? Well, I set up the two expressions, okay, and I say, all right, the rate of 2 over the rate of 1 is equal to 4. Okay, that's been determined from here. So I bring that down here, and then I write the rate expression out, and I say K times 0.2 to the power M times 0.1 to the power N, okay, over K 0.1 to the power M times 0.1 to the power N. You can see that the 0.1s cancel here, and I'm left with 0.2 to the power M over 0.1 to the power N M, which is 2 to the power M. Now, if 2 to the power M is equal to 4, then M must be equal to 2. All right, so I've determined the first coefficient from the experimental information. Now I need to have a look at my table again and say, okay, how can I determine the value of N? All right, so let's do that. Okay, so if we compared experiment 2 and 3 now, because you can see in this case, looking at experiment 2 and 3, I've held the concentration of A constant, but I have doubled the concentration of B. And what has happened to the rate? Well, nothing. It was exactly the same when I started with experiment 2, and when I did experiment 3, I got the same value. So here is the calculation that shows that. Okay, and when I compare them, by doubling the concentration of B, the rate does not change. So effectively then it is 0th order in B. Okay, and how do I get that? Well, here is the rate. Okay, the rate is 1, and if I compare the rate expressions with one another, I can see that I end up with, this is for B, okay, this is for A, right, and I end up with 0.2 to the power N over 0.1 to the power N. 2 to the power N is equal to 1 over here, and therefore N is equal to 0. Okay, so what does this mean finally? Okay, so in terms of this experiment, the rate of reaction for the reaction that we had is equal to Ka squared. I don't include B because it doesn't have an effect on the rate. And in conclusion then, what we can say is we can use any of the data from the experiments in this table here to plug into this rate equation here and find the rate constant. So we can, like I said, choose one of the experiments. This calculation has chosen the value for experiment 1. Okay, so we can then plug the value of the initial rate, which is 1.2 times 10 to the minus 4, and then I can take the concentration that's corresponding, which is this one here, and plug it into the equation over here. And then I can solve for K, making sure that I keep the units very carefully, checking them out exactly how they should be. So here we have molar per second at the top over here, and here we have molar squared. So the units end up as molar to the minus 1 seconds to the minus 1.